Brother, so last time we talked about the fundamentals of power, RF power. We talked about the spectrum a little bit. We talked about a relationship between frequency, wavelength, and the transmission of power. We talked about antennas. We talked about how signals, how information gets onto the RF, and how that RF propagates and how it's received on the other side. We talked about a lot of fundamentals. So I'd like to spend a few minutes reviewing some of those. So we talked about having a transmitter on one side, and that transmitter has to have something to transmit. And then you would have a similar system on the other side, but in reverse, called the receiver. Right. So in its really basic, fundamental form, this is your communication system. Gave some really high-level examples last time of some transmission communication systems that we live with every day. Someone is speaking, transmits the information out of their mouth, out of their lips, and it's different volume, different frequencies in our voices, how we can differentiate between people when they speak. The person on the other side hears the information, receives it through their ear as their antenna, and it comes in through their receiver, it's decoded, and then they understand something. So, in its most fundamental level, a communication system, it takes some type of data through some interface. It could be any interface. We talked about some interfaces last time. It could be a serial interface. It could be an Ethernet interface. It could be a different wireless interface. It could be multiple wired or wireless interfaces. And then the data somehow has to get onto an RF carrier so it can be transmitted. As we said, as an example, we took voice. We said voice is in the kilohertz. And we talked about the fundamental relationship of, everybody should always know this equation, the fundamental relationship between frequency and the wavelength. And we said that these are inversely proportional, obviously. So as the frequency goes up, the wavelength keeps getting smaller. And so with a really low frequency, the wavelength is huge. And so for something like our voice, the wavelength is really, really large. In either case, so when we look at these types of equations, we begin to understand a little bit of the fundamentals of what goes into building a transmitter and building the actual antenna. We said that really low frequencies, really low frequencies, really big bandwidths that makes the antenna really, really large for the really low frequencies. And that's why you don't see a lot of the type of communications that we deal with, from the cellular to the outdoor broadband space, even the indoor Wi-Fi devices that we see transmitted around our houses. Those will tend to be always 2.4 gigahertz and above. Today what's licensed to be used indoors is 2.4 gigahertz and 5 gigahertz. Those are what we call the ISM bands. Those are the free unlicensed bands you can use. In the outdoor space, there's 900 megahertz, 2.4 gigahertz, and the 5 gigahertz. And each of those has its own regulations for power, for what you can transmit and how much noise and interference you can transmit in the adjacent bands. So it's a fundamental equation we want to keep in our heads. But you start here with your data. It could be this voice that I'm speaking, and you have to convert it to an electrical signal, and you have to get it onto this RF. So if you decide you want to transmit, let's say at 5 gigahertz, let's say it's 5.7 gigahertz here, then you have to have a transmitter inside here. And we talked about a really fundamental block diagram that you would take your data, and you would have some kind of a modulator to get your data on, to get it onto a carrier. And then we'll just do some ... You get your baseband signal. depending on what kind of a conversion transmitter you're using, we'll just do a real simple one and just say it's a single conversion. You'll do some filtering, and that's what goes into this box here, this transmitter, this piece right here. So you take your data, you modulate it to get it onto the carrier so it becomes heavy, make it electrical. Then you mix it, you have a local oscillator, you mix it with the baseband to get it to a higher frequency, and now it's in the RF domain. Once it's in the RF, of course, as you know, whenever you do any mixing, you create all kinds of spurs and images and things you don't want to have. So you do some kind of filtering. And then this is what we call the power amplifier, always referred to as the PA. There's a whole lot of little ancillary circuits. I didn't include matching elements and things that we're not going to worry about. We're looking at it from the block diagram perspective. We get it to the RF at the power that we want, and then we send it to an antenna. As we said, the antenna is the frequency selective type of device that we have to spend a lot more time with. You transmit over the air, whatever this distance is, and then you receive it on the other side, just totally in the opposite direction. You have your antenna, it brings a signal into your device, into your receiver, and on the receive side, you do pretty much the opposite of this. We flip all these guys in reverse. You can have like a bandpass filter in front of the LNA. This is a low noise amplifier type of device. You would mix the signal back down, you'd get it into the baseband. Again, I'm not going to include all the filters that would be everywhere, but now you can get your demodulator to pull the data back off of the baseband, and now you have your data back. So this it's just running in the opposite direction. You start here with your data, you convert it into some electrical signal, you put it on your carrier, you increase the frequency of the carrier so you can transmit at this higher frequency, so you can use a much smaller antenna. You transmit the device,